Good evening, guys. I guess we've saved the best for last. All right. It's nearly beer o'clock, not quite yet. So my name is Karthik Prabhakar. I'm the Director of Solution Architecture at Tigera. Tigera is the company behind Project Calico. We also co-maintain Flannel. Calico and Flannel are probably the two most popular network plugins on Kubernetes. Roughly 85 to 90% of Kubernetes deployments use one of these two. We are also the co-maintainers of CNI, which is the network plugin interface used in Kubernetes. So we actually maintain the CNI interface in Kubernetes itself. We are generally pretty active in the Kubernetes networking community. In fact, one of my colleagues at Tigera actually is the co-chair for SIG Network in Kubernetes. So we're pretty, we've been sort of helping grow the Kubernetes networking ecosystem. And so a lot of what I'll focus on today is how Kubernetes networking is fundamentally different than Neutron. And that's a good thing. Because I think if you've heard the talks, not just all day today, presumably yesterday as well, pretty much everyone from CERN to City Network to everyone's talked about how they struggle with Neutron and OVS, right? I'll give you some examples of why that is and why Kubernetes is different. And before I talk about sort of connecting the two together, I'll make a case for the easier it is to connect. It makes it a lot easier to connect the two together if in both sides you have a simpler network to begin with, a simpler and more scalable approach. So I'll give you a little bit of the genesis and history of how we got here, some of the fundamental design principles of Kubernetes networking, and then talk about how you connect Kubernetes and OpenStack. Just show of hands, how many of you guys have sort of dug into Kubernetes deep enough to know things like CNI and services and kube proxy? Okay, so tiny number. Okay. So let me start from the very beginning, right? And if you go back to the early days of virtual machines, someone got the idea that, hey, now we can take traffic coming from this virtual machine, create a virtual distributed switch, put that traffic into a little overlay, and now you have a nice isolated traffic flow that you can take across the network. Almost like the network is something to be worried about or scared about. And as people sort of extended that and took it into the OpenStack realm, as many of you are figuring out now, you now have this sort of concept of creating overlays. Pick your favorite overlay technology, whether it's VXLAN or VLANs or GRE, or it could be BGP MPLS. And you sort of layer on this complex set of bridges, vswitches, plug in IP cables in the middle. And now you have this sort of spaghetti of networking in your OpenStack environment that needs to route packets from one node to another. And it's sort of it's very amusing to see all of you complain about this, but every one of you continues to implement, or 9 out of 10 of you continue to implement this. And for those of you who ever had to operate a network with OpenStack, Neutron and OVS, I mean, this picture will be pretty familiar to you, because you could have packets going out of one VM, destined to a VM on the adjacent node, and yet you don't know what happened, why the packets are not getting there, right? So if you're an SRE, if you're someone that needs to operate a network, and you can't figure out why your packets from VM A to VM B are not getting across, you go back and look at this sort of diagram of what your OpenStack Neutron with OVS actually looks like. Bingo, there's your problem. Right? That said, 9 out of 10 of you, that's what you do. That's the conventional wisdom. It really is the blind leading the blind, unfortunately. So anyway, let's sort of move past that to where we are in the Kubernetes ecosystem. And fortunately, we sort of moved very quickly past the early days of containers when you did things like port mapping from the container to the host to orchestrated environments like Kubernetes. I think we pretty much can take for a fact that Kubernetes has won the container orchestration environments. I think this week Docker announced that they're also going to be supporting Kubernetes alongside Swarm. Mesos announced that they're supporting Kubernetes. So I think we take for a given that Kubernetes has become the dominant platform today. That said, there's sort of some abstractions that Kubernetes brought forward, and you'll find that a number of them actually map very closely to abstractions that Project Calico had brought forward. Partly because the team behind Project Calico was very involved in Kubernetes networking since the early days. And specifically, one of the key abstractions that Kubernetes brought is the concept of decoupling network policy from networking. So unlike in environments like OpenStack and other VM-based environments, where when you needed to isolate two applications from talking to each other, you put them in separate overlay technologies. Typically, layer 2 could be a layer 3 with BGP and PLS, but you put them in separate overlays. And the problem with that sort of overlay approach is as you get more and more dynamic flows, and as you get to an order of magnitude larger, this mess of network overlays becomes unsustainable from an operations perspective. Instead, Kubernetes took a completely different approach, which is to say that it now presented applications with a way to express in a declarative fashion using YAML syntax how they want the application instances to be isolated from each other. So the application can specify using things like labels in Kubernetes that, hey, this is an LDAP server. This LDAP server pod is also labeled production. It's labeled customer A. It is labeled PCI compliant or GDPR compliant. And then you can have network policy that says all objects labeled LDAP clients should be allowed to talk to all objects labeled LDAP servers over port 636, as long as they both belong to customer A and they're both PCI compliant. So you have this sort of concept of network policy that you decouple from networking, which means that in Kubernetes, it's possible to now make your networking significantly simpler. And what it does is it uses a CNI interface, a container networking interface, as the abstraction. You can use different networking plugins. Calico, Flannel are both plugins that plug into CNI. And you'll find the traditional overlay approaches can also plug in. So all of your traditional favorite networking vendors have their traditional overlay approaches that plug in via CNI as well. But the fundamental thing is now that your isolation is being done by a higher level primitive, you no longer have to rely on complex overlays like VXLAN or GRE and trying to encapsulate packets into other packets, lose 50% of your performance along the way, increase your troubleshooting overhead. And so that's sort of a fundamental premise that Kubernetes has taken differently from how Neutron approached it. Of course, there's other premises like things like services and kube proxy. So you can actually abstract away from the fact that Kubernetes is spinning up pods up and down, and yet you have a stable service endpoint that applications talk to, and then kube proxy does the NAT magic to basically redirect traffic to the appropriate endpoint. Right? And other abstractions as well, including things like ingress controllers. You have concepts like kube DNS, but fundamentally, these are all fundamental concepts in Kubernetes. And one of the most recent trends is the use of things like a service mesh with technologies like Istio and Envoy, where you have the concept of having a sidecar alongside your applications. And this was actually developed with Kubernetes, but it's also now becoming available for virtual machines as well. So you can use something like Istio with virtual machines. And the concept is that you have a sidecar that associates a well-defined service identity to your application. And what that enables you to do is now provide things like transparent mutual TLS for application flows. You can do things like transparently do advanced traffic management based on real-time information. You can do detailed introspection, troubleshooting, tracing of your applications. And these are all concepts that a service mesh brings, which is sort of fundamental to the concept of how people deploy microservices, whether it's on containers or on VMs. Okay? But that's sort of a little bit of a sidetrack. And moving forward, if you look at where the industry is going, as you look out into things like serverless or functions as a service, pick your favorite term for it, which is today fundamentally implemented as containers, right? In some sort of a container orchestration platform at the back end. The world is moving to much more lightweight services, which are much more transient, are churned much more rapidly. And this concept of creating a heavyweight network overlay and managing that is something that does not scale in production, certainly as you move forward. So this concept of having these traditional overlays is a technology that is rapidly dying. So for those of you who are still trying to implement isolation using overlays, you may want to stop and look at what's happening in the industry around us. The world is moving away from overlays. So that's sort of one quick assertion I'll make. Sort of switching a little bit and talking a little bit more about Kubernetes itself. So if you assume this concept of multiple nodes in Kubernetes, you typically have this kubelet, which is a little daemon running in every node. And when a pod gets started on a given node by the kubelet, essentially it calls out to the CNI plugin saying, hey, CNI plugin, I want you to get this pod connected to the network. And each CNI plugin tends to take a different approach. We'll talk about how Calico does it here. Calico is a pure layer 3 approach. It doesn't use any bridges or vswitches. It doesn't use overlays. It just does simple IP routing. But the way Calico does it is, first of all, it has a shared key value store, basically a distributed key value store. We use etcd for it, and we can either use etcd directly, or in the case of Calico, you can actually use Kubernetes directly and have Kubernetes use etcd at the back end. So we can actually use Kubernetes as a data store and leverage things like third-party resources, as they're called now, custom resources in Kubernetes. And so the way this flows is when a pod comes up, the kubelet calls out the CNI plugin. The Calico CNI plugin says, OK, I'm going to now create a virtual Ethernet that connects the pod's network namespace into the host's network namespace. We don't use any bridges. We don't use any vSwitches. We just create a virtual Ethernet. And the other thing we do is we then write that workload information into etcd saying, hey, on host 2, I now have pod D, and pod D has a virtual Ethernet. And what happens is we have a daemon running in the host called Felix. Felix sees, hey, there's a new pod that's come up, and it creates a route in the Linux routing table that says, to reach that pod's IP address, send traffic into that virtual Ethernet. Just a simple /32 route. So all we're doing is Felix is just creating a route saying, for that pod's IP, send traffic into the virtual Ethernet. Again, no bridges, no vSwitches, no layer 2 abstractions. We're just doing simple layer 3. Alongside Felix, we have another daemon, a BGP daemon, which creates a full mesh among all the Calico nodes. This is something that is auto-configured by Calico. And what we do is those pod addresses, we advertise to each other, to every other node in the cluster using standard BGP. Why do we use BGP? Let's step back and look at what scales in networking. What is the biggest network out there? Anyone? The internet. What runs internet routing at scale? BGP. What is the simplest routing protocol there is? BGP. So we just use standard BGP to exchange routes among different nodes. So all we're doing is we are sharing container or pod routes with other nodes. Typically, we aggregate them, so you're sharing /26s. And that's what we use for the routing protocol exchange between nodes, which we create as a full mesh. If you want, you can use route reflectors and the more advanced recipes. But we keep things very simple. And so fundamentally what Calico does is it creates routes in the Linux routing table that says, this pod's IP address is reachable via this node's IP. And from that point on, it's the standard Linux routing function that happens. Without encapsulation, no overlays, it's standard IP routing. So when you look at packets and troubleshooting, there is no mess of bridges and vSwitches, no complex overlays, it's simple IP traffic. Now, the other thing that goes hand in hand with that is the policy part of it. Because now we're just basically saying every pod can talk to every other pod, but you need to provide isolation. And for that, Calico also provides a full implementation of Kubernetes network policy. In fact, when you look at Kubernetes network policy, it's a mirror image of Calico's, because the Calico team actually helped develop network policy for Kubernetes. And it's one of the sort of canonical implementations. And so when an application gets deployed in Kubernetes, the application specifies network policy in the form of, hey, LDAP servers should be allowed to talk to LDAP clients as long as they have the label customer A, or production, or staging, or pick your favorite labels. So you have labels and label selectors. And essentially what Felix does is it looks at a pod when it comes up. If the pod's labels match network policy intent, it then creates an IP tables rule at the virtual Ethernet connecting to the pod that says this pod's IP should be allowed to talk to the set of IP addresses that matches what the policy says. And we do that as a single IP set rule, so we encapsulate all of these different IP cables rule in a single lookup in the kernel. So essentially, we do that microsegmentation at the virtual Ethernet level, connecting to the pod. And what that means is, from a networking perspective, everything is super clean and simple. We do that policy isolation at the point at which the pod connects into the network. Super clean architecture, super scalable. And sort of, if you look at what network policy looks like in terms of how this is presented to Kubernetes as part of the Kubernetes pod spec, this is what is typically presented. So in this example, for example, you have a label that says this policy needs to apply to anything labeled database and anything labeled PCI compliant. And the policy says that on ingress to that pod, any traffic from applications labeled front end allowed, as long as that application is also labeled PCI compliant. And on the egress, you're basically saying allow everything. So you have policy of this kind that you declare as part of the application's pod spec, which is what happens in Kubernetes. And from that perspective, that policy is enforced, but the networking itself is super clean, right? Now let's sort of segue into OpenStack. There's sort of different approaches you can take with OpenStack. For connectivity, obviously, Neutron with OVS is one approach. Calico, here's a clue. The Calico architecture is completely different. This is sort of mirrors what we do on Kubernetes, which is you have the concept of virtual machines, and in the case of virtual machines, we're using tap interfaces. But fundamentally, we use policy to define what to isolate from each other. We treat every node in the cluster as a routed node. Every node is a router. So we're doing IP routing. And Calico simply programs the routes into the routing table using a BGP daemon. So again, from a connectivity perspective, same architecture, do the microsegmentation at the point in which the tap interface connects into the host, and keep the networking really simple. So fundamentally, a very different architecture compared to what most of you are used to with OpenStack, which is complex layers of bridges and vswitches, and complex overlays connecting nodes with random layer 2 paradigms. So this is a fundamentally different architecture. There is one other thing we do, is we actually do also have a local DHCP agent, partly because we found that when you get to hundreds of nodes, DHCP and how it interacts with DNS mask puts some fairly heavy load in Neutron. So we actually have an optimization for that as well. But fundamentally, it's the same approach. Unlike in Kubernetes, where we use a CNAP plugin, in OpenStack, we run as a Neutron plugin. So we are absolutely a Neutron plugin, but it's a pure layer 3 approach. And unlike OVS, where you now have to deal with something like DVR or VRRP to backhaul stuff into an L3 agent, in this case, every node is a router, so there's no sort of backhauling. Every node can forward traffic directly, whether it's to the outside or whether it's east-west traffic. So a very clean architecture, if you will. And so from that perspective, as you step back and look at different approaches before we get to how we connect OpenStack and Kubernetes together, if your OpenStack environment looks like this, with Neutron and OVS, I would say good luck. You're going to have some challenges. We'll talk about some of the approaches that people take, which is using things like OVN or Courier, but fundamentally, you're building on top of something like this and adding some more complexity. And then you have to deal with the concept of how you get past your overlays, fight your overlays to connect into Kubernetes. Now take this sort of Neutron with OVS picture. The corresponding picture for Neutron with Calico would be this. Every node's a router. Every VM obviously gets one or more IPs. We create IP routes in the Linux routing table and do normal forwarding, and then use policy. Actually, in the case of OpenStack, unfortunately, we cannot use full policy because OpenStack does not have sort of a rich policy language like Kubernetes does. What OpenStack has as security groups. So what we do is we map a security group into what we call profiles in the Calico policy hierarchy. So we basically take a security group and map it into that same sort of policy hierarchy within Calico, right? But fundamentally, the architecture is every node's a router. And what we do is we create routes in the Linux routing table and do standard BGP to exchange routes between nodes. So that's sort of the Calico architecture from an OpenStack perspective. So now when you start talking about how you connect OpenStack and Kubernetes together, certainly when you start with, say, Kubernetes running on bare metal and you want to connect up OpenStack to it, here's what we do. We have a shared data store. In the case of Calico, we use etcd. And from a networking perspective, all we need is IP connectivity between your Kubernetes environment and your OpenStack environment. It could be on different sides it could be on different racks. It could be in different sides of your data center. One could be in your data center. Your Kubernetes environment could be in a public cloud somewhere. It doesn't really matter. All you need is IP connectivity. And what Calico does is enforce the policy that says what should be allowed to talk to what based on a richer policy language. So if your label says only applications labeled customer A and labeled PCI compliant should be restricted to talk to other pods labeled customer A and PCI compliant, that's something you can enforce in policy. But the networking is super clean. We're not encapsulating packets. We're not creating sort of overlays. We're not giving you additional performance overhead of cutting your performance by 50% by putting IP packets into Ethernet, into UDP, back into IP, back into Ethernet. It's just IP packets. Troubleshooting is super simple. When you guys troubleshoot connectivity failures on your laptops, you go start off looking at your MAC address, looking at whether your switch is responding? No. You do a trace route. You do a ping. That's what you do with Calico. You do pings, trace routes, and it's IP routing. We know how to do IP routing at scale. So that's fundamentally the Calico approach in terms of how you connect Kubernetes with OpenStack is we use normal IP routing, and then we use policy to define what can talk to what. And by the way, here it showed OpenStack and Kubernetes. It doesn't even matter if some of the nodes that need to talk to other applications, where some of your applications are running on host instances or bare metal. You can run Calico in host protection mode, where Felix is doing that policy protection on the host interfaces, as opposed to the container or VM interface. So you can actually run a Felix in policy-only mode, where you're using the same set of labels, except now the label is associated with maybe a database running on a Linux bare metal instance. Or it could be an instance running in the cloud. Or maybe you don't even want to run Calico on a node, but you know this node happens to be a mapping service that you want to connect in. And in that case, you know the IP address. And all you do is you'll sideload that policy into Calico's data store that says this IP address is a mapping service, and this mapping service should be allowed to talk to any other pods or VMs that are labeled mapping, right? So it doesn't matter whether your application is in Kubernetes, VMs on OpenStack, host instances, or running instances in the cloud. It's all a matter of simple policy. So from a connectivity perspective, again, this is about keeping the networking simple and using policy for isolation. And so if you look at who's using Calico today, this is actually just a small sampling. I'll give you some examples from this. I talk about, in the abstract, I talk about sort of different use cases for Kubernetes with OpenStack. One is what I showed here, which is Kubernetes running side by side, where you're running Kubernetes on bare metal with OpenStack on bare metal, and the two of them running side by side. That's certainly a fairly common use case. The second sort of scenario is where you're running OpenStack on bare metal and Kubernetes running inside the VMs. And in the case like that, from a Calico perspective, the connectivity is fairly trivial. All we do is peer the BGP in the inner layer with the BGP in the outer layer. From a networking perspective, it almost looks like a top-of-rack switch to the inner layer. So the outer layer's BGP looks like a top-of-rack. So it's just BGP peering. It's one routed hop. That's it. Networking, again, is fairly simple. Another example is the other sort of scenario is where now you're running OpenStack as a containerized application on top of Kubernetes. This is something that AT&T is doing, for example. So what AT&T do is today they are running OpenStack on bare metal, but what they're moving to, the next generation architecture, involves Kubernetes on bare metal. They have containerized their OpenStack control plane. So every OpenStack service like Nova, Neutron, Swift, Lance, name it, it's all been containerized. And they're running it as a containerized application on top of Kubernetes. Specifically, they use a project called OpenStack Helm, which encapsulates all of those OpenStack control plane services as a containerized application and creates a Helm chart for deploying it on top of Kubernetes. And what that means is they're now able to deploy OpenStack on top of Kubernetes using OpenStack Helm, and then things like upgrades are orchestrated by Kubernetes. So what they do when they need to upgrade from, say, Mitaka to Newton, this is something we did together at the last OpenStack Summit. We did a presentation there. You go into the Kubernetes manifest, change the version from Mitaka to Newton, and upload the new manifest to Kubernetes, and Kubernetes takes care of upgrading every OpenStack service on the fly, making sure that you have sufficient resources so there's never an outage. So it's sort of a live upgrade from one version to the next within a matter of like 4 or 5 minutes. In fact, at the last OpenStack Summit, the guys at AT&T did a live lab with about 200 people that all did that upgrade, which was pretty fascinating to watch. But what they do is they use Calico for networking in the Kubernetes layer, keep things very simple. And then the OpenStack layer, pick your favorite plugin. In their case, they're actually using Contrail for some of their customer applications for some of the service function chaining requirements. But the architecture itself is very simple and clean because now Kubernetes knows how to do lifecycle management of applications, including OpenStack as an application, and being able to upgrade it from one version to the next. So that's the scenario where now you're running OpenStack on top of Kubernetes as a containerized application. Again, a very simple architecture as long as your Kubernetes architecture is clean, which in the case of Calico it would be. That's just a few examples. Today, Google actually used Calico as part of Google Container Engine, so GKE actually runs Calico. IBM run Calico as part of their hosted Kubernetes offering. Box actually have a mix of Calico and Kubernetes, but also in the case of Box, they also use Calico for protection of host instances. In fact, Box have actually replaced all of their physical firewalls by Linux boxes running Calico, just because their physical firewalls are running out of TCAM space. So in this case, they actually use Calico as their firewall, because now they can use Calico's policy-based protection and protect against Kubernetes pods, or put Kubernetes pods running in the cloud and connect them and allow connectivity to stuff they might be running on-premise, and sort of being able to do all of this in a common policy-driven model, but without using overlays, using simple IP connectivity, right? And so this is sort of a number of examples, and in fact, I think the most recent survey of actual adoption of different network plugins in Kubernetes will, I think the top two, so both Flannel and Calico, by the team here at Tigera. But obviously, even Google use Calico. So if you look at sort of the adoption, the majority of Kubernetes deployments today tend to use this Calico policy engine, irrespective of whether it's Calico networking underneath or something like Flannel, or even other SDN approaches, like, for example, some cloud providers use. Like, for example, IBM, they use Calico behind the scenes, but as far as the customer is concerned, they just get connectivity. So let me sort of pause there, because the other approaches that you have in connecting Kubernetes with OpenStack, there's a few other approaches I'll sort of call out here, and then maybe take a question or two. If you start with a clean OpenStack architecture and a clean Kubernetes architecture, and assume things like, in Kubernetes, for example, you assume that every pod has an IP address, and that IP address is unique across the cluster, and you keep your networking clean, then connecting pods to VMs is trivial. If, on the other hand, you have a complicated OpenStack architecture, which unfortunately the majority of OpenStack deployments do today, you now have to start worrying about how do I get traffic out of my VM, back through my sort of L3 agent, and then get past the overlay into the Kubernetes environment, and then start looking at going through a Kubernetes ingress architecture. It's a whole different level of complexity. People have approached this. There's sort of what I would call a number of science projects going on. There are people who are trying to take the approach that, hey, one way to solve this game would be to take Neutron and plug that into Kubernetes as a CNI plugin. That's the approach being taken by, say, the Courier project. The challenge with that is if you step back and think about this, Kubernetes networking is designed to work at the scale of hundreds of thousands of pods a second, right? Neutron, you're lucky if you get 4 to 5 VMs a second. Neutron is a fairly heavyweight platform. You look at the database synchronization in Neutron, every little operation in Neutron requires a database sync. Now, when you start taking a heavyweight system like that and plugging it into Kubernetes, what sort of scale do you think you're going to get? So that's one approach that people are working on in the community. Another approach that people are working on is this concept of, hey, we have Neutron with OVS. Let's layer on a database on top of that and make the database do all the calculations, which is what's happening with something like OVN. How many of you have been around in networking for, say, 25, 30 years? Show of hands. Anyone? No one? Go back and look at some of the history books on networking. I hate to say it, but I was around in designing large networks in the early 90s. Remember this sort of battle at the time between what was then TCP/IP and IP routing versus, at the time, something called X25 and X500, which was supposed to be this grand database that unified everything. So the X500 database did all your network calculations, and then the X25 created this circuit switched network throughout your network. Now think about what OVS and OVN is. It's this concept of having a circuit switched network and then a database, specifically OVN, that sort of does all the calculations, versus what used to be the IP routed approach, which is assume that your network is never going to converge. There's always some instability in your network, but your IP routing sort of dynamically creates paths through your network. And that is sort of the approach that not just Calico, but any IP routing protocol takes. There's also sort of approaches to bring together things like fairly complicated SDN controllers, whether it's Open Daylight or others, and have this SDN controller sort of manage this calculation. So whether it's a database or an SDN controller, pick your pick. But fundamentally, it's assuming that you have some centralized piece of logic that has complete visibility of the entire network, and at any given time, it says the network is stable. That's a very different approach than what Calico is taking, which is assuming that IP routing works at scale, which it does, and going, hey, we're just going to use IP routing. We know how to scale IP networking. We're just going to use IP networking and keep things simple, right? So those are the two approaches, and I mean, there's lots of humor if you look at the IETF docs on poking fun at people that think the centralized controller is going to work. Maybe it will. If you're a large telco and you're used to having that level of complexity, go for it. But I think what's happening in the real world is that as people are adopting Kubernetes at scale, which they are, they're finding that keeping networking simple, especially operationally, is critically important. And so that's why you see things like the adoption curves as you do with things like Calico and Flannel, and you find a lot of the sort of science projects way down in the developer-focused areas, right? So that's sort of the trends today. Let me end there. I know I'm sort of a little over time, and I'm keeping you from your beer. Maybe a question or two. I'll also be around for the beer, so I can sort of chat then too. Any questions on anything I've talked about?
I'm Karen Nielsen. I'm sorry, I wasn't here in the beginning, so this question may be really stupid. But you say that the IP routing scale. What about IP addresses? Is there an implicit assumption here about using IPv6? Or?
So Calico works with both IPv4 and IPv6. In fact, if you look at our Twitter feed, there have been a number of people who blogged recently about their success in getting Kubernetes working with v6. So Calico on OpenStack has always supported v6, works fine, so you take your pick of v4 or v6. Kubernetes, there is certain different abstractions. Calico does the pod-to-pod networking, which works fine with v6, as we've proven. But there's other elements of Kubernetes that don't work with v6 yet. Specifically, kubeproxy still has some issues with v6.
I'm also just merely trying to make the point that your point about scalability, I mean, you can only make that point together with IPv6. I mean, because one of the reasons that we have all these tunnels and overlays and underlays
Yeah.
is because of the scarcity of the application for
Understood.
space. Okay.
Yeah.
So I just think it's an important point to make.
Yeah, so that is absolutely an important point. So the way you do that today in Kubernetes is, by the way, I would never be someone to preach NAT if you don't want it. In fact, I would say avoid NAT if you can, because NAT typically introduces more problems. But generally speaking, when most people deploy something like Kubernetes or OpenStack, they tend to use a private IP address range for applications within the environment, typically a 10-dot space. And all they're doing is, with something like Calico, they're routing that 10-dot space or 192 or whatever the private address range is within the infrastructure. As long as you're routing tables and can handle addresses, and you have that working within your infrastructure, that's great. But point taken, the moment you have to go across into the internet, something like IPv6 is sort of inevitable. And this is where Calico supports IPv6. We do strongly believe in v6. Kubernetes has a little ways to go to catch up on a few remaining artifacts that are not yet v6 ready, but I think it's pretty close. Kubeproxy is actually fairly close, and and work is happening there. It should be there shortly. Good.
Okay. Yep. So one more short question, so let's see if I got it right. So when you have VMs in OpenStack to integrate with Calico, do they need to have unique IP addresses even for private networks then?
Correct. So there's some fundamental assumptions that Calico makes, and this is sort of in lockstep with Kubernetes networking as well. So Kubernetes makes the assumption that every pod has an IP address, and that IP address is unique across the cluster. Calico makes the exact same assumption. It assumes that when you assign an IP address, that IP address is unique across the cluster. We actually hold that assumption forward in OpenStack as well. So today, Calico does not support overlapping IPs. You might think you might find service providers that might have a problem with that, but believe it or not, many of the large service providers that have deployed Calico are perfectly okay with that, because as people move into the cloud space, they assume they are getting an IP address as part of that cloud deployment. And there actually are approaches that can be taken for Calico to support v6. We thought we'd have to implement that. We had 0 requests so far to support things like overlapping IPs. So the Calico model is that when you deploy an application, your provider, whoever is operating the network, assigns the IP address. In the case of Kubernetes, we have something called Calico IPAM that does the IP allocation in an efficient manner. In the case of OpenStack with Neutron, we actually have Neutron do the IP address allocation. Just because it makes it easier for Neutron to do things like the database synchronization, Neutron gives Calico an IP address to assign to a VM, and that's what we assign to a VM. But that IP address is unique across the cluster.
So one more related, thanks for your answer there.
Sure.
So you have, in the picture, when you included a physical machine into the Calico network,
Yeah.
I assume then you would need to trust that machine to use the right IP address, because otherwise it could hijack the network, so to speak.
Yeah, so actually what we do in the case of physical machines when you're using Calico is to protect that physical machine is we turn off the networking portion. We assume that if this is a physical machine that's been provisioned, it already has an IP address. All you're doing is you have Calico policy that's protecting the physical interface on that machine. So you use the same set of label primitives as you might be using in, say, Kubernetes and other places, tied to the data store, which has etcd certificates. So you need to have some sort of role-based access control that says this physical machine is performing this function, has this labels. And those role-based access controls are tied to whatever policy you define for that physical machine. But the networking, we actually don't do anything on the net. We don't do the BGP. We don't do any IP addressing. We just assume the machine has an IP address, and it's being given now a bunch of labels that we protect using policy. Okay. Thanks.
Any other question then?
So enjoy your beer, guys.
Yeah.
One sort of call to action I'll have is go back and think about this. One link I forgot to put here, if you actually go to projectcalico.org, by the way, Calico is 100% open source. There's actually a pretty active Slack channel. And believe it or not, we are literally every major, not all, but many of the major OpenStack deployments that have happened over the last 2 or 3 years, especially the ones across thousands of nodes, they're finding that Neutron with OVS doesn't scale for them operationally. So they're actually in the process of working with us, and many of them are in the process of transitioning to Calico. So, but this is actually still well-known secret in that a lot of people in the OpenStack community don't know about this. There's still people blindly just doing, hey, OpenStack, we just do Neutron at OVS, even though it is operationally messy. So go out, learn about this, join the Slack channel, try it out. One caveat I'll give is Calico doesn't, not all the installers integrate Calico. It works with OpenStack Ansible, it works with Juju, it works with DevStack, a few others, but it doesn't, I mean, there's a few other installers where it doesn't work yet. Try it out and let's start building more community here. That's ultimately the goal for doing these presentations. We want to start building out this community of people that are thinking about networking, as opposed to just blindly doing what someone else did 3 years ago, because that's the only thing they know. Learn about this, talk about this, share your experiences. Okay, thanks, and meet you guys at the beer.
So thank you very much.